Imagine standing on the shore of another Earth. The sky above you is blue. Clouds drift slowly across the horizon. A warm sun rises over a quiet ocean. The waves move the same way they do here. The light feels familiar. The year lasts 385 days, almost the same as ours. This is how many people imagined Kepler-452b when it was announced. A rocky world, orbiting a sun-like star, at just the right distance. Not too hot, not too cold. Headlines called it Earth 2.0. And for a moment, it felt like something extraordinary had happened. It felt like we had found a second chance. Another place where life might exist. Another place where oceans might shimmer under a distant sun. From far away, Kepler-452b seemed comforting, familiar, possible. But space has a habit of being more complicated than headlines. Because when you look closer, not at the artwork, not at the name, but at the numbers, the story begins to shift. Slowly. And then completely. Kepler-452b is not just similar to Earth. It is bigger, about 60% wider in diameter. That may not sound dramatic at first. 60% doesn't feel extreme. But on a planet, size changes everything. A bigger planet means stronger gravity. Stronger gravity means thicker air. Thicker air changes how heat moves, how clouds form, how weather behaves. On Earth, our atmosphere is balanced in a delicate way. It traps enough warmth to keep oceans liquid, but not so much that the planet overheats. Change the gravity, and you change the balance. Even mountains would be different on a world like this. Surface pressure could be higher. The sky might feel heavier. And if Kepler-452b is rocky, which scientists believe is possible, it may weigh several times more than Earth. That much mass doesn't just sit quietly. It reshapes how a world functions. Let's think about that gravity for a moment. It doesn't just hold down air, it holds down rock. A more massive planet means a more compressed interior. Higher internal pressure could mean a thicker, more rigid crust. On Earth, tectonic plates move. They slide, they crash, they cycle carbon back into the mantle. This deep cycle acts as a planetary thermostat. It prevents our world from suffocating in its own gases. But on a world with potentially 5 times Earth's mass, that crust might be locked tight, stagnant, unable to breathe. If the thermostat is broken, the atmosphere absorbs every change and holds it. Already, the picture is less simple than Earth 2.0. But size is only the beginning. Kepler-452b does not orbit our sun. It orbits a star that looks similar, but is older, about 6 billion years old. Our sun is younger, and stars change as they age. They grow slightly brighter over time. Not suddenly, not dramatically, but steadily. That steady increase matters. Today, Kepler-452b receives a little more sunlight than Earth does. Just a little. Around 10% more energy. 10% sounds small, but in climate, small changes rarely stay small. A little more warmth means a little more evaporation. A little more evaporation means more water in the air. And water vapor traps heat. More heat means even more evaporation. This isn't an explosion, it's a feedback loop. And feedback loops don't need to be dramatic to be powerful. They only need to continue. This is the silent reality of celestial mechanics. A star does not care about the stability of the worlds orbiting it. It simply fuses hydrogen. It simply radiates energy, and the planet must absorb it. Imagine the equator of Kepler-452b. As the star matures, the tropical zones expand. The mild latitudes are pushed closer to the poles. Ice caps, if they existed, begin to retreat. Less ice means less sunlight reflected back into the dark. More sunlight is absorbed by bare rock and open oceans. Another loop, another quiet shift in the equation of survival. Imagine oceans that begin to warm, not boiling, not disappearing overnight, just warming over thousands of years, then millions. More water rises into the sky. The atmosphere thickens slightly. The planet holds on to heat a little longer each year. Nothing catastrophic happens in a single moment. Instead, balance slowly tilts. On Earth, natural processes help regulate temperature. Rain falls, Carbon is stored in rocks. Heat escapes into space. But these systems depend on oceans remaining stable. If oceans shrink, even gradually, those regulating systems weaken. And when regulation weakens, warming no longer corrects itself as easily. It begins to compound. This isn't speculation about disaster. It is how climate systems respond to long-term change. And Kepler-452b has had more time under a brightening star than Earth has. Time matters. When people talk about the habitable zone, they often imagine a fixed ring around the star, a safe region where water can exist. But that ring moves. As a star grows brighter, the safe zone shifts outward. Planets don't automatically move with it. They stay where they formed. Billions of years ago, Kepler's 452b might have been perfectly positioned. Oceans stable, mild temperatures, clouds drifting across calm skies. But as its star slowly brightened, the balance would have shifted, year by year, century by century, million by million. A planet does not need to leave the habitable zone suddenly to begin changing. It only needs to sit near the inner edge long enough. And Kepler-452b may have been sitting there for a very long time. There is something else about water. When a planet warms enough, water doesn't just evaporate. Some of it rises high into the upper atmosphere. There, intense radiation from the star can break water apart. The lightest part, hydrogen, can escape into space. Once it escapes, it's gone. A planet cannot easily rebuild oceans after that. This process does not happen overnight. It unfolds slowly. If Kepler-452b has been receiving slightly more energy for an extra billion years compared to Earth, it may be further along this path. Not dry, not necessarily lifeless, but changing. And change over long enough time becomes permanent. For years, Kepler-452b was described as a promise, a place we might one day visit, a reminder that Earth is not unique. But perhaps we were looking at it the wrong way. Maybe it is not a younger Earth. Maybe it is not a twin at all. Maybe it is something far more interesting. A planet that began like ours, with oceans, with balance, with stability, but one that has simply had more time under a gradually brightening star, more time for warmth to build, more time for small shifts to accumulate, more time for irreversible changes to begin. We often search space for another Earth because we hope to find a mirror of ourselves. But Kepler-452b may not be a mirror. It may be a preview. Earth will not remain exactly as it is forever. Our sun will continue to grow brighter. Not tomorrow, not next century, but inevitably. Over immense stretches of time, oceans here will also begin to change. Evaporation will increase. Heat will accumulate. Balance will shift. Life on Earth exists within a window. A long window, but still a window. Kepler-452b may simply represent a world further along that same timeline. Not destroyed, not apocalyptic, just older. Time is the ultimate variable. We are obsessed with finding the right distance, the right size, the right temperature, but we often forget to account for the right time. A planet is not a photograph, it is a moving picture. This does not mean Kepler-452b is barren. We do not know its atmosphere. We do not know if it still holds oceans. We do not know its surface temperature. It could still be temperate. It could still be stable. But the combination of its size and its star's age suggests something important. It suggests that habitability is not permanent. It suggests that even Earth-like planets evolve, and that evolution does not stop at perfect. It continues, slowly, quietly, relentlessly.
Kepler-452b is about 1,400 light-years away. The light we see today left that system long before modern technology existed on Earth. We are looking into the past. And yet, in a way, we may also be looking forward. Because what makes Kepler-452b fascinating is not that it might host life. It is that it might show us what happens to Earth-like worlds after billions of years under a steady, brightening star. It reminds us that planets do not stay young forever, that stability is not a permanent state, that balance can drift. Kepler-452b was once imagined as Earth 2.0, a new beginning. But perhaps it is something else entirely. Perhaps it is Earth 1.5 billion years from now. Not a second chance, but a future chapter. And that possibility makes it far more profound than any headline ever did.